Welcome, Eshik Boys High School students, and a very special hello to Mr. Jager's physics class. You've tuned into For the Love of Physics.
So you've been looking at some really key ideas in class, right? Stuff about fluids, pressure, and temperature. Today, our deep dive is all about making those ideas, well, click. We want to connect them to the real world, make them less textbooky and more, exciting.
Exactly. And it's important stuff. I mean, understanding fluids is everywhere. It's the air we breathe, the tech we use. You really can't escape it. These ideas are fundamental.
Totally. Okay, so let's start with pressure. We know the definition, right? Force per unit area. P equals F over A. But what does that feel like? You actually feel it all the time. Think about diving into a pool, that pop or pressure in your ears.
Oh, yeah.
Or driving up a mountain, same thing happens.
Right.
Or even on an airplane.
Right. That's the fluid, water, or air pushing on you.
Exactly. Or think about a knife. A sharp one slices an apple easily, yeah. But a dull one, you gotta push way harder. Why?
Same force, different area. Precisely. The sharp knife puts all your force onto a tiny, tiny edge. Huge pressure. The dull one spreads it out. Less pressure. More squishing than slicing.
Good example.
And that leads to those, amazing deep sea suits, like in Figure 9 to 6 in your book.
Oh yeah, the atmospheric diving suits. Incredible engineering.
They have to be strong because the water pressure deep down is just immense. The deeper you go, the more water's pushing down.
It's a fantastic illustration. And speaking of spreading force, think about snowshoes.
Okay.
You step in snow with just boots, you sink, right? Yeah. But pop on snowshoes, you stay on top.
Yeah.
Why? Your weight, the force, it's the same.
The area. The snowshoes spread the weight out.
Exactly. Bigger area, much less pressure on the snow, so
Yeah.
you don't sink. It's all about how you distribute that force.
Cool. So when we measure this pressure stuff, what units do we use? In physics, the main one is the Pascal.
Pascal.
Right.
1 Newton of force spread over 1 square meter.
Yeah, 1 × 87. But a Pascal is actually pretty small, isn't it?
It is, yeah. The air around us right now, that's about 100,000 pascals pressing down.
Whoa. Okay, so saying 100,000 pascals all the time is a bit much.
A little cumbersome, yeah.
So we often use another unit, right? The atmosphere or attotemum.
Much more convenient for everyday pressures. 1 attotemum is basically that 100,000 pascals or 105 psm.
So my car tire pressure, maybe 3 attotemum. That's like 300,000 pascals.
Roughly, yeah. Around 3 times atmospheric pressure. Your textbook, Table 9-2, has some wild examples.
Oh, yeah.
Pressure at the center of the sun. Something like 2 times 10 to the 16th pascals. It's mind-blowing.
Wow. Okay, that puts things in perspective.
But what's really fascinating, I think, is how we handle atmospheric pressure.
Right, you said it's like 100,000 pascals. That sounds like a lot pushing on us.
It is. It works out to about 200,000 newtons on an average person. That's like
Yeah.
having a couple of small cars sitting on you.
Seriously, how come we don't just, get squashed?
Huh. Good question. It's because the fluids inside our bodies, our blood, the air in our lungs, they're pushing out with the same pressure.
So it balances out.
Perfectly. It's an equilibrium. We're built to live in this pressure cooker, basically. Amazing, really.
Okay, so that's pressure itself. But how does it, travel through a fluid? If I push on water in a bottle, what happens? This is where it gets really clever and useful, thanks to Blaise Pascal.
Pascal's principle, yes.
So Pascal's principle, what's the simple version?
Basically, if you have a fluid trapped in a container and you push on it somewhere,
Uh-huh.
that pressure gets sent everywhere inside the fluid. Equally, undiminished, to every single point and even the container walls.
Okay, squeezing a toothpaste tube.
Perfect example. You squeeze the bottom, the pressure travels all the way through, and paste comes out the top.
Right, or pumping up a bike tire.
Yep. The air you pump in pushes out evenly on the hole inside of the tire, not just near the valve.
Makes sense.
And this principle, it leads to some seriously powerful tools, like the hydraulic lift. You've probably seen them in garages lifting cars.
Oh yeah, definitely. Figure 9 to 7 in the book shows one.
Right. So the magic here is you push with a small force on a small piston or area. Yeah. That creates pressure. Pascal says that same pressure goes through the fluid to a big piston with a much larger area.
And since pressure force area, if the pressure is the same but the area is bigger?
The force has to be bigger too, much bigger. You multiply your force, that's how a little push can lift a heavy car.
Wow. That's force multiplication.
Uh-huh.
F1 over A1 equals F2 over A2.
That's the math behind it, yeah. Small force, small area equals big force, big area. But it makes you wonder, doesn't it? If you get this huge force out, what's the catch? What are you trading for it?
Good question. Like you don't get something for nothing in physics, usually.
Exactly. Think about maybe how far you have to push the small piston compared to how far the big one moves. Something to mull over hints at energy and work later on.
Interesting. Okay, let's shift gears slightly. Still talking pressure, but
Yeah.
how does it change when you go deeper? Like, picture a submarine diving down, down, down in the ocean.
Okay, getting deeper.
What happens to the pressure on it?
Well, it's going to go up, right? There's more and more water sitting on top of it.
Exactly. All that water has weight, and weight is a force. So more water above means more weight, more force, more pressure.
Which is why subs need super strong hulls.
Definitely. So the pressure increases with depth. We call the total pressure down there absolute pressure.
Absolute pressure. Okay.
And it's basically two things added together. First, there's the pressure already pushing down on the surface of the water.
Which is the atmospheric pressure we talk about, P0.
Right, P0. Plus, you add the extra pressure from the water itself due to its depth.
Gotcha. So P0 plus the water's contribution.
Yeah, and that water part depends on how dense the water is, how deep you are, and gravity. You might see it as P0 plus rho.
Rho GH, density, gravity, height, or depth.
Yep, rho is density, H is depth. The main point. Deeper means more rho, so more total pressure.
And that P0, the atmospheric pressure, it's just the weight of all the air above us, right? Like a giant column reaching way up.
All the way to space. It's invisible, but it's definitely there.
And we measure it, classically anyway, with a mercury barometer, like in figure 9.9.
How does that work again?
Well, you have a dish of mercury and an upside-down tube of mercury sitting in it. The air pushes down on the mercury in the dish, and that forces the mercury up into the tube. How high it goes tells you the air pressure. Pretty neat way to see an invisible force.
Cool. Okay, so we've covered pressure quite a bit. Force, area, Pascal, depth. What about the other big idea? Temperature. How does temperature fit into this picture, especially with fluids like gases? We feel hot and cold, but what is temperature in physics?
Right. It's more than just a feeling. It's about the particles themselves.
The kinetic theory of gases view.
Exactly. Think of gas particles like air molecules as tiny little balls bouncing around constantly super fast.
Okay, like microscopic billiard balls.
Sort of, yeah. Zipping and colliding. Temperature, fundamentally, is a measure of their average kinetic energy.
Kinetic energy, energy of motion. So higher temperature means
The particles are moving faster, on average. Zipping around with more energy. Lower temperature, they're moving slower.
okay. Faster movement means higher temperature.
And if we tie this back to pressure, think about it. If the particles are moving faster,
They'll hit the walls of the container more often and harder.
precisely, more collisions and more forceful collisions means more force on the walls over the same area, which means
Higher pressure. Aha! So temperature and pressure are linked through particle speed.
absolutely linked. Heat up a gas in a sealed container, its pressure goes up because the particles are banging against the walls harder and more often.
That makes sense. Like maybe honey. When it's cold, it's super thick and slow to pour.
Right, high viscosity.
But warm it up and it flows easily. Is that related?
Definitely. Warmer honey, the particles have more kinetic energy. They can slide past each other more easily. Lower viscosity, same idea with engine oil needing to be warm.
Or even like a hot air balloon.
Perfect example. Heat the air inside, particles move faster, push outwards, the air expands and gets less dense than the cool air outside.
And floats up. It's all connected.
It really is.
Now, measuring temperature, we usually use degrees Celsius, degree.
Common scale.
But in physics, especially with gas laws and kinetic theory, we often use Kelvin, K.
The absolute temperature scale.
Yeah, and the conversion is easy, right? Just add 273.
Pretty much. Kelvin Celsius plus 273. So room temp, say 20 degrees C, is 293 K.
Okay, so quick question for everyone listening, especially Mr. Jager's class. Imagine two rooms. One is 20 degrees C, the other is 22 degrees C. In which room do the air particles have more average kinetic energy?
Think about that link. Temperature is average kinetic energy.
Exactly. So higher Celsius means, higher Kelvin means faster particles, the 22 degrees C room.
You got it.
Okay, well, we covered a lot. Let's quickly recap. We started with pressure force per area, feeling it in pools and with knives.
And snowshoes. Don't forget the snowshoes.
Right. Then Pascal's principle, how pressure spreads out equally, making hydraulics work.
Force multiplication. Very powerful.
Then we saw how pressure increases the deeper you go in a fluid, like water or even the atmosphere.
P equal plus R croc. Absolute pressure.
And finally, temperature. Not just hot or cold, but the average kinetic energy, the speed of the particles.
And how that speed directly connects back to pressure and gases. Faster particles, higher pressure. Okay, so here's a final thought to chew on using these ideas. Imagine you have a sealed plastic water bottle, like you bought it down near the sea. Then you take it up a really tall mountain. What happens to the bottle? Does it change shape? And why?
Ooh, good one. Think about the air pressure outside the bottle versus the air pressure inside the bottle at sea level and then on the mountain. Definitely discuss that one. These physics ideas are everywhere. Stay in contact with your physics teacher. Stay creative.